for geological studies. Sir, please.
Thank you, Dr. Rajat Chatterjee, for inviting me to just briefly talk about these two methods, how they are being used, and then, of course, the more details will be provided in the subsequent lectures. So, as many of you are aware that, when we talk of geospatial technologies, we are basically talking about remote sensing, we are talking about satellite communication, we are talking about GPS technologies, and then basically each of this technology is being used for environmental integrity, natural resource development, human development indicators. So many of these technologies today coming together to provide large amount of information about the natural resources, their distribution, and then of course there are certain host of environmental issues also which are basically being tackled using these technologies. So these technologies are also, you are aware that they are being used for addressing various sustainable development goals, which has been envisaged by United Nations and by the government of India also, for socio-economic security, for food, water, energy, health, shelter, infrastructure, for information, as well as for sustainable development like impact assessment, resource conservation, ecosystem management, climate change, then geosphere, biosphere studies. Disaster risk reduction is a big area, and especially we have large amount of geological disasters also where the key role of this geospatial technology is also there. So we talk about the preparedness, we talk of early warning systems, and then how best we can provide response to the disaster when the disaster has happened. And this technology is also being used, for doing large amount of disaster, recovery as well. Then there are issues which are related to planning, monitoring, evaluation, and decision support as far as the governance related issues are concerned. So conventionally, many of you must be using a lot of what we call, when it comes to the Earth observation data, it is basically known as the multispectral data sets. The power of this conventional remote sensing is that we can collect the reflected energy from the Earth's surface in different broad channels which are basically distributed across electromagnetic spectrum. So many of you must have been aware about Landsat, about LIS3, LIS4, A-wave sensors, which has typically 4, 5, or even like models. They have more than around 10 or more than 10 spectral bands, which are basically having a broad bandwidth. Okay, so as of now, many of us are exposed to this type of multispectral data sets, which basically have spectral range covering somewhere from 70 to 400 nanometers and collect the reflected energy from surface of Earth in these broad bands, typically in 4 or 5 spectral channels. But of late, this convention is basically now being replaced, or also, what I say, is being augmented with more information about the Earth's surface in narrow spectral bands, which is of the order of around 5 to 10 nanometers in terms of spectral resolution, and the number of spectral bands are also very high, from hundreds to 200 in that range. So what it means that you are able to get very precise reflected spectrum of Earth's surface across the electromagnetic spectrum in more or less continuous manner, rather than in discrete manner when it comes to the multispectral data sets. So this is what we show you here, that you have this typical electromagnetic spectrum starting somewhere in the near UV at around 0.3 micron, and then going all the way up to 3 micron or so into the infrared region, and then of course the far infrared region. And what you see is this small dips here basically is nothing but the transmission lines which are caused by the absorption due to the atmospheric gases which are present in the Earth's atmosphere. So we try to do sensing through these atmospheric transmission channels in more than 100, 200 bands in a continuous manner, where the typical bandwidths are of the order of 5 to 10 nanometer. And such type of imaging strategy or imaging sensors which are developed, they are typically called spectrometers or hyperspectral observation system. So rather than having 4 or 5 bands, you get a stack of bands, and this basically you can mimic like stack of cards, the playing cards. There are 52 cards in a deck. So similarly, you have more than 100 or 200 spectral information associated with each pixel, which basically gives you the reflected spectrum of that particular pixel, which may be composed of different material like vegetation or bare soil or water pixel. And that information provides you what is known as the spectral signature of that particular pixel at that spatial resolution. And these typical characteristics of a particular surface can be precisely estimated by this spectral signature, which you get from 0.4, so let us say up to 2.5 micron. In this case, this is a typical spectra for vegetation. So you have this peak at around 5 micron, where the leaves becomes they looks like green because they reflect heavily in the green part of electromagnetic spectrum. They absorb strongly in the red band, and then again they reflect very strongly in the near infrared, and then small humps are basically caused by the absorption due to the water vapor, or maybe due to some other pigments, etc., which are present in the leaves. So if you can characterize this full spectrum using this hyperspectral technology, other than mapping, you can also do quantification of various geophysical variables or biophysical variables, which basically contribute to this spectral reflectance curve. So these technologies has been flown, as I was telling in the inaugural thing, also from space, from airborne platforms, and from ground-based platforms also. These things are there. So as far as the Indian Space Research Organization is concerned, we have flown some experimental hyperspectral satellites called on IMS-1 platform, then this HISES, which is an operational remote sensing, hyperspectral remote sensing sensor, currently also operating at 30-meter resolution. Then along with ISRO, NASA, we have also done a campaign which is basically known as the IIRS campaign, where from the aerial platform, the hyperspectral data has been acquired at selected sites, for various ecosystems, and these data sets have been extensively used for various purposes. Now, this is just a brief about the IIRS campaign site all across India. This is the IIRS sensor, how it looks like. This is the IIRS team. This was basically put on this NRSC aircraft, and then for natural ecosystems, water bodies, snow, ice, geological targets, natural hazard related aspects, coastal targets, inland water bodies. We also targeted coral reefs. So over variable type of targets, large amount of this hyperspectral data from this IIRS sensor was being collected, and it's available with ISRO for doing large amount of research activities which are devoted to this hyperspectral data utilization program. Then, just to tell you the details of this pack, this is how the data cube looks like, because why we call it cube, because it has not only the 2 dimensions, but there is a third spectral dimension is also involved. So for each pixel, of this image, let's say 512 by 512 image, you have huge amount of spectral data sitting behind one particular pixel. So these are some of the examples of the spectra acquired for various targets. So you have this, the target, which is vegetation target. Then this brown spectra is basically for the bare soil. And then this is the spectra where less amount of chlorophyll concentration, or you can say the degraded vegetation is there. And then, of course, there are absorption lines, which are basically related to various aspects like leaf water, the cellular scattering, which is basically controlled by the nitrogen, and the chemistry, which is present in the leaf structures. And similarly, this is how the spectrometer works, that it has an area array detector, there is a grating system here, and there is a light collecting telescope, and then line imaging is done. As the platform moves, you start getting the 2-dimensional data sets out of this particular sensor. So once you acquire the radiance data, this radiance data needs to be converted into the reflectance data. So this red line is nothing but the data collected at the airborne platform, and then the blue line is the data which is basically normalized and converted into what we call as the reflectance. So there is a little bit technical difference between the radiance and the reflectance. So this is the typical reflectance curve for vegetation. This is the typical reflectance curve for the water body. Then this is the typical reflectance curve for the soils, as well as for the bare soil and the soil which has got some mineral compositions also. So different type of surfaces can be characterized very clearly using this airborne hyperspectral data sets. So this is a classical example, especially in geology. The hyperspectral data is being used for mineral targeting, and this particular example which you see over here, where clearly the alterated minerals has been identified using various absorption lines. There are spectral absorption lines associated with different minerals. I will not go into details of this because there will be a separate session on this. But these absorption lines are typically characteristics of, let us say, presence of water, or presence of iron, or presence of even carbonates bearing structures. There will be a specific line. So like that, by combining these data sets and by processing this data, you can generate maps, where certain amount of mineral compositions or different mineral compositions can be extracted very precisely. This is again another example of, the Udaipur region, where also you can see that over this area, using a data processing technique called the spectral angle mapper, different, mineral assemblages and mineral compositions have been identified. Now, these are some of the examples of one of the space-borne sensor which is flying today on in the orbit. It is developed by ISRO. It's called HYSIS. It also has a spectral resolution from spectral range from 400 to 2500 nanometer. It operates 10 nanometer spectral resolution with a spatial resolution of 30 meter. This is the data, the kind of data cube we get from this India's HYSIS satellite. And this is how different channels looks like. This is a movie of all the channels, and you can see how the spectral variability is there in different channels. Okay. So some of the initial bands in many of these hyperspectral sensors, they are a little bit noisy, but there are also very good bands which are available for analysis. So this is how the total spectra, the radiance spectra looks like from the HYSIS mission for different pixel locations. And then you can also create different band combinations, the different for color combinations. So this is a typical false color composite of an area somewhere in Ladakh, where you can see this is somewhere in the eastern Tibet region, and this is a river here, so you can very clearly see the water, and then of course the vegetation and all those things. Similarly, you can make combinations of various spectral channels and generate different type of color, false color composites also, as well as quantitatively you can generate the spectra of different surfaces. So this white color spectra is the spectra of vegetation. Then this yellow color is the spectra of water. Then there is also a runway seen over here. So this is a concrete here. So this is how the concrete spectra looks like. It's much flatter. And then this particular concrete spectra, and then the runway is basically dark in color because it is made of, the darker material, and that's how the reflectivity is much lesser compared to the concrete surfaces. So you can see that using our this HYSIS data also, we are able to extract the spectral signatures of different objects, and we can characterize the material type also based on the type of material which is present at this location. So this is another band combination, as I was telling you. That was a combination typically known as the false color combination. But here what I show you, a band combination of SWIR bands at 2200, 1600 and 930 nanometers. This looks pretty different. But here you see that certain objects, they become very, contrastingly they come up. So you can see this bright features over here, which was not to be seen when we were looking the spectra, the false color composite of this area. So one can use this many number of bands to generate different type of combinations, and different information will get highlighted in these combinations. So we just did some detailed analysis and found that what are these brighter features. So these brighter features, when we looked into the high resolution images, we found that they are nothing but the solar panels. So they had a very peculiar spectrum compared to the contrasting vegetation over here. So like that, in the entire scene, we can then could identify using a technique called the mixture tune match filter, the locations of these solar panels as well as the concrete structures. So this becomes a very unique property where a specific feature becomes much, even though it is very small, somewhere there this solar panels are very, very small inside, but we are able to extract them based on their spectral properties. Now, just coming to briefly to the SAR systems, you see, SAR also is being used extensively for geological studies for many decades. But the current advances is essentially India is developing a joint SAR mission with NASA. It's called NASA ISRO SAR mission, which has two frequencies, L and S band. India is developing S band and NASA is bringing the L band. And we have developed an airborne version of this as a precursor to NASA mission. So there is a airborne L and S band SAR system is available, and these are some of the images of this L and S band SAR, which is basically being flown at different parts of India as well as in US, and you can see this different features. Similarly, we are also having this airborne system. So many of you must be aware about the RISAT-1, which was flown in 2012, but currently there is no, after that it stopped after giving some useful data for some few years, and then this year, in the month of February, again we launched a satellite called ES4, on which there is a follow-on sensor for this RISAT-1. It's known as RISAT-1A. So this is the most recent image of this RISAT-1A, and this is a combination of different polarimetric versions, the combinations of different polarimetric channels, HH, HB, and HH by HB. So this is how you see that many of the objects, they bear the different colors. So this data will be available. A very good quality data has been, is coming from this RISAT-1A, and I'm sure that you will be using soon this data for various applications. As far as the applications of SAR in geology is concerned, it is used for various aspects like structural mapping, lithological mapping because of the dielectric variability of different minerals and rocks, then mapping of geomorphological features, mineral exploration, and active fault mapping. This is also being used for assessing, the slow-moving geological disasters, especially using interferometric mode data sets for earthquake-related or associated, the crystal deformations, as well as the deformations which are associated with volcanism. There is large amount of land subsidence happening at various locations, either due to the extraction of groundwater or oil, or maybe due to coal fires, or maybe in coastal areas because of some other processes. So these type of very small or fine scale land subsidence also can be monitored using these type of SAR systems, and there will be certain lectures in detail which will be providing you this information. So currently these SAR systems are available in different frequencies. We have X-band SAR, which has a wavelength of around 3 centimeter. We have C-band SAR, of the order of 5 to 6 centimeter wavelength, and then the L-band SAR, which has a longer wavelength and it has much more higher penetration capability. So all these multi-frequency SAR systems, either from India or from foreign satellite operators, currently the data sets are available. Depending on the application which you are foreseeing, the frequency selection becomes pertinent. Now the basic advantage, as you can see, the SAR systems provide this because it has longer wavelength, it can penetrate to this cloud. So this is an optical image. You can see there are a large amount of clouds in this image, but when you see the corresponding radar image, because of the larger wavelength of the radar systems compared to the cloud particle size, the wavelength is able to pass through, and then you get large amount of, the total surface of Earth basically, which is basically a cloud-free coverage. So this is the basic advantage over the optical systems, and especially for a country like India, it becomes very useful during the monsoon season, etc., for doing flood mapping. Now the structural map, as you can see that there are large amount of geological structures. All of you are maybe from geology background. You can see that these structures, compared to the optical images, they come up very strongly on the SAR data sets. And this is one example of NOAA SAR, which is basically an S-band SAR launched by India, operated by a UK company. You can see around the India or the Kurdwar region how the structural details of various rock forms in this area, and some of you will be able to identify some of these linear features or faults, etc., as well as the fracture zones across this region, where you have very unique geology, where it is basically the beginning of Himalayan system, and such type of data sets are very, very useful for especially for geological applications. Then, of course, as I was telling you, because of the owing to the penetration capability, large applications of this data has also been there in the detection of this buried paleo channels, especially in Rajasthan and the Haryana area. A lot of work has been done where the the buried paleo channels, which can be very useful, or they are conduits of water also, especially in desert region. If you identify them, they are potential reservoirs of groundwater accumulation. So this data is also been found very useful in such application. Another interesting aspect is this oil seep detection, especially in coastal areas or offshore areas for oil exploration. So these oil seeps, basically, they look like very linear, curvilinear features in SAR images, and some of this spills may be happening due to the natural spillage from the oil reservoirs below the ocean bottom, and then once the oil floats onto the surface of the seawater because of its buoyancy, some of it can be detected by the SAR images, and then the exploration geoscientists, they use this as a signature for finding the hydrocarbon reservoirs also in offshore regions or in the coastal regions. So these are some of the examples of interferometric applications where the deformations associated with various processes can be quantified in a very precise manner. And then large amount of work has also been done. Our IIRS team, Dr. R.S. Chatterjee and his colleagues, on detecting and monitoring the deformation in North India, especially in Haryana region and Delhi region, due to the groundwater extraction. So I'm sure that these type of examples also will be dealt in much more detail in subsequent lectures. One of the exciting mission which is going to come up by next year is a joint ISRO-NASA SAR mission. It's called NISAR mission. It has, as I told you, two frequencies simultaneously available, L-band and S-band. So that is a unique characteristics. It has various other technological aspects, data available in different polarimetric mode, as well as there will be opportunity to do large amount of time series analysis, especially for deformation, and a very precise interferometric products are also being defined. So this is a very exciting data which is likely to come for various Earth system studies, and the data will be made available free of cost to all the researchers across the globe. So I think many of you will look forward for this excellent data, which is going to come up in two different frequencies from from single platform, and this will lead to a lot of science-related, studies on the dynamics of ice, both in Antarctic, Arctic region for ice sheets, glacial velocities, then of course climate change related aspect, especially the sea level rise, etc. Because if you can assess the melting rates of these ice sheets, probably one can also compute the sea level rise. Then for biomass changes in our forests and in agricultural systems, solid earth deformations, especially aseismic, co-seismic or post-seismic deformations, as well as just before the volcanic eruptions. If we can monitor these deformations, probably it will also help us in assessing the risk associated with active volcanoes. And then, of course, the cryospheric studies, disaster response, especially the flood and then earthquake and maybe landslides also nowadays people are targeting with time series interferometric observations. And of course, various other geological applications which we just talked about. Many of these data sets are going to be immensely useful. So look forward. Probably by this year end or maybe in the early next year, there can be a launch of this 9 ISR mission. And of course, the capacity building and training is very important, and the IIRS is continuously doing it along with CSSTAP, and this particular training is also an example of that, we are very much there to help you out solving your doubts or any other issues which you have in using these advanced technologies for your research applications, research and applications. What is on horizon? So of course, as I talked, the very high resolution remote sensing data, especially less than 25 centimeter, all weather imaging, microwave data and its applications are going to be now forerunners in times to come. And of course, there will be also satellites which are being planned from the geostationary orbits, which also provide you high spatial as well as spectral resolution data sets. So Government of India has also unleashed reforms in space sectors where more private participation and by youths in terms of startups, etc., is being encouraged. So all these newer technologies, especially hyperspectral and SAR, has a lot of potential, especially for young generation, to even start business enterprises. So with this, just a brief overview, I would like to close over here and thank Dr. Chatterjee and his colleague for giving me this opportunity. Thank you.
Good afternoon, everyone. So this is the first or the basic lecture for the hyperspectral remote sensing, what we are talking about, and its uses for the geology. So I will be telling you a little bit about what exactly the hyperspectral remote sensing is. And first of all, we'll start with for the geology, how the remote sensing is used in one or two slides. Then we'll go that what are the advantages of hyperspectral over the multispectral and what are the basic uses that can be some of the sensors, hyperspectral sensors also what can be used for the geological applications and so on. So let's go with it. So when we talk about remote sensing or remote sensing for geology, so generally when we do the geological mapping also, or for the mineral exploration or for the lithological mapping or other characterization of the soil or rocks, the thing is the classical mappings or classical geological mapping, it is very tedious, very time consuming, and for tough terrain or for the remote or the heterogeneous terrain, it is very, very, very difficult. So with the help of remote sensing, it is comparatively easier with the limited human observations. What we can do, we can play the very important role in the mineral exploration as well as some lithological characterization or some geomorphological characterizations and all. The advantages of remote sensing when we are talking about for the geological application, for the panchromatic or the multispectral remote sensing, it deals with the bird's eye view. Basic advantage of remote sensing is the synoptic view. We can view the terrain from the top. So what happens when we are able to view it from the top, we can see or we can have more interpretation comparative to the part when we are standing on the ground. So we cannot see as far as when we are comparative to the remote sensing data when we see from the top. So the understanding of the terrain, the regional geology of the area is better understood using the image captured. The image may be panchromatic, it may be multispectral, and with the advances the microwave images or hyperspectral images. So when we are seeing the image, the multispectral remote sensing has the advantages as compared to the panchromatic, and the hyperspectral has the advantages over the multispectral imaging. Now, so when we see the multispectral data set, what are the things we are able to do using the multispectral remote sensing data for the geological application, for the geological overview point of view. So basically we can do the regional analysis of the area, that will provide us the clues to the direct areas of interest for the mineral exploration or for other applications. Like this is for the mineral exploration. Now for the geomorphology, it provides the detailed area geomorphology of the area. It can be for the useful for the ore guide. We can identify some alteration zones that can also used as the local guides for the exploration or for understanding the geology of the area. Then you can have the structures or the lineaments or the faults or the folds can be seen, which are exposed on the surface, can be seen clearly using the multispectral data set and can be used as the input for the geological application. Then when we talk about mineral exploration or the minerals identification, there are some guides. Generally we talk about structural guides, lithological guides and botanical guides. So structural guides will basically takes care of the structures present on the image, for example lineaments, faults, folds. Then lithological guides will tell about the lithology of the area, what are the different lithologies present in the area, and that can be clearly marked using the multispectral images. And third comes the botanical guides. So botanical guides are basically the anomalies in the vegetation or the forest areas or the trees present in that area, and those anomalies are because of the presence of some concentration or some typical pigmentations in the leaves, or those are because of the change in the composition of the soil, or if the soils are enriched in a typical or particular material or particular mineral, then those changes appeared in the leaves or the vegetations present in the area. So in such a way, when we talk about multispectral, the lithology, the structure and botanical, three guides can be easily understood for the mineral exploration, and we can understand the geology like structures, like lithologies present in the area using the multispectral data set. Now this is just an example because it's just an overview. So using the multispectral or the ASTRO data set, as I have told you that some ratios can be generated. So just if you see this image, this is the ASTRO image of some Umra Rajasthan area, and in this there are different colors visible in that, and if you see carefully you can see some folds also in this, like just below the, if you can see the number 5 over here, so below there is some nose of fold is visible, and some other structural features are also visible. But this ratio is basically generate color composite of the ratios. So they are RGB. These three colors are used to generate this FCC composite ratio. In this, red color has been given to the ratio 4/6. Band number 4 is divided by band number 6 of the ASTRO image. Then, and that band, the resultant band has been given the green color gun. The green color gun has been assigned to that band. Then band number 5/6 green and 7/6 blue. So like this, there are three different ratio images were generated: 4/6, 5/6 and 7/6. And by combining these three, a single color composite, single FCC was generated, which is shown over here in this slide. And this composite image of ASTRO data, ASTRO satellite acquired in April 2003, this says it highlights the absorptions. Basically, when we generate the ratio, when we are generating the ratio images from any satellite data, what we are doing, we are trying to divide the absorptions present in which we are interested to, we are trying to keep the high reflectance at the numerator and divide the absorptions, or we are keeping that absorption of that particular material in the denominator. So what we are doing over here in this, we are dividing 4/6, we are dividing the band number 4 by band number 6, as we want to highlight the clays. We want to understand more about the clays present in that area, and the clays shows the absorption in the at the band number 6 of the ASTRO data. So our 4/6, 5/6 and 7/6 basically highlighting the clays, but the 4, 5 and 7, these are the different like kaolinite, muscovite, N-Sarasate light, which shows the high for the different or the respective like muscovite, kaolinite and elite minerals. So like this, when we see this, the high clays or the in this area, the altered minerals were highlighted, and some of the vegetation parts are also highlighted, and all those which have got absorption in band 6 and high reflectance in 4, 5 and 6 are correspondingly or accordingly respectively highlighted in red, green and yellow colors. So if we summarize it, so remote sensing imageries, these can be used to map the lithology, faults, fractures, to recognize the hydrothermally altered rocks by their spectral signatures, and to be directly we can map the mineralogy, mineral abundance by using manually the hyperspectral imagery. So these two second and third topic for the identification of hydrothermally altered rocks and the mineral abundance can be done mostly using the hyperspectral imaging technologies, but initial some polygons or some zeroed in areas can be obtained using the multispectral ratio images, and those ratio images will be used as the subset for the whole area, and those or the interested areas, and those particular imagery which are highlighted using the multispectral will be thoroughly investigated using the hyperspectral imaging techniques, and the mineral mapping, mineral abundance maps, or the identification of the minerals or the materials present in that area will be done using the hyperspectral imaging. Now, first of all, we'll say now we understood that now what is the role of multispectral and what are the advantages of the hyperspectral over multispectral will be discussed in the next slides. So the definition comes over here. What exactly do we understand by the hyperspectral imaging is, it is the acquisition of images in hundreds of contiguous registered spectral bands such that each pixel, from each pixel we can generate a radiant spectrum. So this is the definition by Goetz. It's very initial persons or very founder of the hyperspectral remote sensing that these person has started the imaging spectrometry. So he said that we can generate the spectrum of each pixel. So that's why this is also known as the imaging spectrometry. Like if we use the spectroradiometers, field spectroradiometers, so what we do, just by holding these spectroradiometers, we are able to get a spectrum of a material or a mineral which are present or in which we are interested. We are taking the spectrum of. Now, the same spectra can be obtained using the hyperspectral images. But here, the spectra of each pixel, it won't be like in the spectroradiometer. What we do, the area exposed to the sensor, or the FOV, small FOV of the sensor, or if it is in contact, then the radius of the contact probe will be the area for which we are getting the spectrum. In this, the hyperspectral imagery, we will get the spectra of one pixel. That pixel may be the mixture of different classes, or it may belong to one particular class. So with the help of hyperspectral remote sensing, we are able to generate the spectra of material. So that's why it is also known as the imaging spectrometry. So all the spectrometric analysis, what we are able to do using these spectroradiometers, we are able to do the same things, almost same things, using the hyperspectral imaging. So the purpose of this, as it is clear from the definition, that we are able to generate the spectrum of each pixels, and that spectrum can easily be compared with the spectrum of the spectroradiometers what we have. That's why it is also known as the imaging spectrometry. Now, what is the difference? So the difference between the multispectral, conventional multispectral and the hyperspectral remote sensing is, in the multispectral remote sensing, we are basically generating the spectra. If you see over here in this slide, you can see very carefully, in the panchromatic it was only one band. In the multispectral, we are generating the spectrum, or we are collecting the information or radiance or reflectance of the present surface in few spectral bands, but the typical characteristics difference is these bands are discrete, these are not continuous. There are gaps in between, and we are generally collecting the spectrum, collecting the information of the surface of the earth in the atmospheric windows. So the band number 1, 2, 3, 4, 5, 6 or so, those bands are designed in such a way that the effect of atmosphere is minimum. So we are basically collecting the information in the atmospheric windows. So the region where the effect of atmosphere is minimum or negligible, only those regions are selected. But in the hyperspectrum, as we want to generate the contiguous spectrum, so we cannot go like selecting these bands in such a way that we'll select in, say for example, band 0.4 to 0.6, and then we won't be taking 0.6 to 7, and then suddenly we'll 0.4 to 6, then we'll jump from 0.8 to 9. We cannot do this, because if we'll arrange the bands in such a way that we won't be able to generate the spectrum of each and every pixel, and that spectrum we need the continuous observations in all the spectral bands present in the hyperspectral data. So the two important conditions for the hyperspectral data set is it should be contiguous and the bandwidth should be very narrow, so that the if the bandwidths are very narrow, then what will happen, the typical absorption features, like when we are dealing with the spectrometry or when we are trying to identify the minerals or the materials present on the surface using the spectra, then we have to deal with the spectral profile of the material. And that spectral profile, the important part of the spectral profile are the typical absorption features which are present, which are peculiar or characteristic of each and every material. That depends upon the composition and the crystal lattice structures of the material. So if the bandwidth will be very broad, then some of the spectral features will be like it will be smoothened. But if we have very narrow bandwidth, then each and every spectral features what we are interested in will be thoroughly mapped, and we'll get thorough points for each and every spectrum bands whatever available with this, and the spectrum will be smoother, and we'll be able to identify the material using the typical absorption dips by the hyperspectral images or hyperspectral spectra what we are trying to generate using the image. So differences in the multispectral, number of bands will be few, but the bandwidth will be more. In the hyperspectral, bandwidth will be very less and number of bands will be very high, like hundreds, 100, 200, 400 or so. And there should be no gap in between. The spectra should be contiguous. So it is just an example you can see over here as we are talking about the geology. So this example is also from the rocks present or the minerals. The white color spectra what you can see over here is the spectra of dolomite. Now when you study in these next few lectures, you will come to know that the dolomite, because of the composition, it has got the typical absorption features because of the presence of CO3 at 2.3. Now if you see over here, because of the Landsat TM7, it doesn't have a band over here at 2.3. So the spectra of, say, this white spectra of dolomite, this green of montmorillonite, this yellow of elite, and all those spectra except this gypsum, the pink color one, all look similar. They all are similar. We cannot differentiate just by seeing the spectra that what these minerals are. But when we talk about the hyperspectral spectra or the spectroradiometer spectra, whatever spectrum we will get, you see over here the dolomite has a different absorption dip. The calcite, it has got an absorption dip around 2.3. Then there are different absorption dips we can see over here, and by seeing the spectra also, if we know about the characteristic absorption dips of the material, then, or if we know how the absorption dips are forming in that particular material or the mineral, we can see over here carefully that these all 4, 5, 6 spectra are different. They have got different absorption dip at different positions. So their spectra is typical, their spectra is peculiar, and just by seeing those spectra or identifying those peculiar absorption dip, those minerals can be identified using the hyperspectral remote sensing. So the basic advantages is identification of the material, whereas the multispectral, we are not able to identify, we can just map, we can just see the material over here, different materials in different colors, but here we can pinpointedly, because of the presence of absorption dip, we can identify each and every material, or each and every material which consists of 1 pixel, because we won't be able to do much when it is subpixel. We can up to some extent, but at least it should have a pure spectra. So we should have a pure spectrum can be generated, and those minerals which are consist of them can be identified. The materials which are consist of them can be identified clearly using the hyperspectral images. Now, this is the example of an mineral alunite. You can see over here, this is the spectrum what we will get using the Lancet TM. So there are 1, 2, 3, 4, 5, and 6 we are getting using this Lancet. In this MODIS, there are number of bends are more, but still the absorption dips are present over here at 1.4 because of the presence of OH stretch over here in this, and this 1.4 is absent. You do not have even that band which is covering the 1.4, because that 1.4 is the water absorption band, and that water absorption band present is absent in Lancet TM and in MODIS. So in general you can just shape the curve of alunite, but identification of alunite mineral or any mineral which has got absorption dips, typical absorption dip in between these points where the bends are concentrated, is impossible using the multispectral data. But using the spectroradiometer or the hyperspectral lab, what do we have? Or using the imaging spectroradiometer spectra, when we are able to generate the spectrum of the minerals of the pixels, we can identify or we can understand the absorption dips present in the material, and those can be used as the identification for the materials without being in contact with that particular point. But yes, it doesn't mean that we do not have to cross-check the things in the field. We do. It is must. We have to go to the field. We have to cross-check the things, but we do not have to. The field work is essential, but seriously, it has been reduced. So we can do the mapping using the remote sensing data set, but we must have to go to the field to cross-check the results what we have obtained through it. How to visualize, as the director sir also mentioned in the previous lecture also, that hyperspectral images, we sometimes refer to them as the image cubes because they have got a large number of measured wavelengths. So the hyperspectral imagery, basically it is collected as a data cube. So this data cube, what exactly the data cube says? There are X and Y plane. In that X plane and Y plane says the information about the location of the pixel, whereas the Z plane says about the spectral information. So let's see in the slide. So if any pixel over here, which you can see in this hyperspectral data cube, this is the typical characteristic example or the site which has been used since very long. The hyperspectral sensor has been evolved for the Jasper Ridge, California. You can see over here, there are different pixel locations and basic classes can be seen. There are some vegetation, some roads, settlement, water classes, dry river beds, and all those features are able to see. We can see over here. There are some lineament features are also visible if you see carefully over here. So just for an example, right now it is the land use class forest. If you want to generate the spectrum of the class forest, like the right topmost corner. Then that right topmost corner of the pixel, the XY location says the location of this pixel and how it is appearing, and the Z direction you can see over here in this rainbow color. This Z says what are the values of this pixel in each and every band. As this is the example of the IIRS data set, it has got 224 number of bands. So the values of this pixel in each 224 band, each band which has got 22 to 4 in number, is recorded in Z direction, and this is showing over here in this just the rainbow color. It is just the representation of the data set. Generally the Z direction has been studied just by using the or generating the Z spectrum of the material. So for each and every pixel, for all the pixel, what will we do? We will generate the spectrum and we will be able to see the spectra or the spectral behavior of that pixel in all the bands. So this is the same. The X, Y and Z axis, what I have already explained. X axis is the X and Y is the pixel location and Z is the spectral location. Now, when we are dealing with the multispectral data, the FCC or the standard FCC combination is fixed, like 432 or 321, whatever, according to the IIRS. Now, but when we are dealing with the hyperspectral data, the bandwidth is very small. So for the red region, red wavelength region, there are 10 or 12 or 20 bands available. For the green region, again there are 10, 12, 20 bands available. For infrared region also there are number of bands available. So the bands for each color unlock, for red, for green or for infrared also, there are different bands available. So whenever we are making any FCC of the hyperspectral data, ideally we should mention the band numbers. Like for this, R, G and B is band number 43, 17 and 10. These three bands has been used. I can use it 40, 30, 20 also. Then also I will be able to have some FCC. If I will use this 40, 20 and say 12 or 13 also, then I will also have a FCC. So according to my use or according to the best result I am getting or the best bands available in this infrared, red and green region, I am taking the bands for my FCC combinations, and accordingly I am writing and giving the details in the data whenever I am generating it. Now, as the reading of the spectral curve is important, because whatever we are doing for the hyperspectral data set is basically we are trying to study the spectra of each pixel. So for studying the pixel, for studying the spectra of each pixel, most important is the understanding of the diagnostic absorption depths and their locations. So whatever diagnostic absorption locations and depths are present for each and every mineral in the spectrum, that has to be studied carefully. So there are several mechanisms responsible for this. In the subsequent spectroscopy classes, there will be one class for the spectroscopy and how these spectra are formed of all the minerals and rocks, and what are the different basic absorption mechanism will be studied. You will be able to understand those different mechanisms like crystal field disturbances, charge transfer, conduction band shift, color center absorptions and vibrational process, different processes which govern the typical absorptions present in the different material and their chemical compositions. That will be given in the subsequent lectures. Now this is just the example, like there are three main classes present over here: soil, vegetation and water in an image. So the soil spectra will look like this, the vegetation will look like this, and water will look like this. Now just by seeing the spectral properties also, you can say that vegetation will have absorption in red and suddenly very high in infrared, and then sudden absorption and all. So by seeing this spectra, you can say that this belongs to the spectra of the vegetation, which is consists the chlorophyll. Okay. Now for the water, if we are talking about water, will have the reflectance, high reflectance in the visible region, and after that it is almost absorbed and we will get the values almost close to the zero. In soil, again it depends upon the composition. Here, if it is wet soil, we'll have that absorption dip at 1.4 and 1.9, and depending upon the composition, it is rich in like kaolinite or montmorillonite, or accordingly wherever it is the content or the chemical composition or the geochemistry of the soil will let us know about the spectrum of the material. So now in very brief about the basic hyperspectral sensor what we have. So there are different spaceborne sensors and airborne sensors also. So I am basically listing over here the spaceborne sensors like Hyperion. So it was launched in 2000 by NASA. Then CRISPR, then MERIS, it is INVISAT, and their spectral resolution around 10 nanometer, 5 to 10 nanometers. This IIRS we were talking about. This is the airborne sensor. It is still working, and now we are getting the IIRS NG, the new generation IIRS sensor, and this has got the 5 nanometer spectral resolution, and their spatial resolution, as it is airborne, it depends upon the height on which it is flowing. So recently this PRISMA data is also there in 2020, launched by ASI. It is almost same or the same, the parameters are almost same as the Hyperion. Hyperion, HYSIS and PRISMA, almost same parameters, launched by the different organizations. And the recent one is the PRISMA. We will be getting this, the data is also available. So for studying different, like for the hyperspectral studies, for the geological application or for any other application, you can register, and this PRISMA data can be downloaded. This IIRS, what we are talking about over here, is basically Chandrayaan 2 onboard sensor. And it is also a hyperspectral sensor. The bandwidth is the range is 0.8 micrometer to 5 micrometer, and the spectral resolution is 20 nanometer, and spatial it is 80 meter. So these are the different parameters what we have. Generally, it has been known for the hyperspectral sensors. Only main sensor I have included. There are some other sensors also which can be included. Now, what are the applications? So the applications other than geology are also numerous for the atmospheric, like water vapor, cloud properties and aerosols, then ecology, chlorophyll, leaf water, cellulose, pigments, lignin, all these things. For geology, identification of minerals, identification of lithology, different soil sciences, then for different mining, all those applications are there in geology. For snow and ice, what are the snow cover fraction, their grain size and melting, all those applications are there with the snow. Then coastal waters, the chlorophyll content, phytoplanktons, dissolved organic materials, suspended sediments, and all those features can be, all those classes can be derived using the coastal waters also. Then using the biomass burning, what are the temperature, smoke, and all those things can also be studied using the hyperspectral data. Then if you are talking about the commercial, yes, with the mineral exploration. So nowadays lots of mineral exploration companies are also using the hyperspectral data for the initial surveys. They are using multispectral data for the initial surveys, and then those areas which they have got zeroed in or they have identified, those areas they are very carefully observing and studying using the hyperspectral sensors, hyperspectral data set. Then in commercial, this agriculture and forest production also can be studied, can be seen. The crop growth monitoring can be done. The stress in the crop or stress in the vegetation or trees can also be monitored using these hyperspectral sensors. So as far as again we come to geology, the geology is very, very much important. And the hyperspectral remote sensing is very, very much important for the geological exploration because of its unique spectral characteristics of many alteration in rock forming minerals. As I have told you that the minerals which are present, they have got very typical characteristic spectra or the absorption dips present in the different ranges, and because of that, those rock forming minerals, those minerals, if they constitute a pixel, if they are present on the surface or some surface signatures present such as gosans and all, or the altered products present on the surface, can be identified clearly or easily using the hyperspectral remote sensing data. That's why it has very significant, it has made a very significant contribution to the field of exploration geology. Just one more example of this area again. This is the Hyperion image, what we have seen in the northern Grapevine Mountains, Nevada, California. Over here, in this, this is the true color composite what they have tried to make using the band number. Again, they are mentioning the bands 31, 20, 10. These are the wavelengths. And this is the mapping method. Using some mapping method, they have mapped some pixels which constitute of the different minerals, clays present in that area. And again, when we are doing the classification or pixel mapping in the multispectral data sets for the land use or land cover, generally we say that there should be very less or almost zero unclassified pixels. But when we are talking about geology and when we are matching the spectral profile of different minerals present on the surface, we get number of unclassified pixels because all the pixels present on the surface do not have the same spectral property in which we are interested in, because the surface or subsurface geology is also covered with the land use and land cover features present on the surface. So we will get few classified pixels. As you can see over here, there are different classified pixels. They are just wrapped over the true color composite images. In that, the green color, this is the muscovite. Then the blue muscovite too, they have two classes. They must divided the muscovite into two, green and blue. Then there is calcite, then dolomite in yellow color. The calcite or dolomite also mixing at some places because of the few common spectral properties. Then some silica is also present in the purple area and some zeolites in the cyan color. So like this, these are the different pixels which has currently which has been classified correctly using the mineral map, and this mineral map is used using the spectral angle mapper algorithms. So in the next class tomorrow, we will see the processing techniques what we are using for the classifying the or the mapping the minerals in the hyperspectral data, what are the steps to be followed, and so on. So that's it for the today introductory lecture. Thank you.
Dr. Harish. TNP team.